Hello, this is a video for day 33. Hopefully you all have a somewhat filled in note sheet in front of you. I'm going to fill in the missing pieces because I think it's easier to explain as I do it rather than just talk through it. And hopefully this will make sense. Today we're looking at some more examples with trig derivatives, and then we're going to talk about something called the chain rule. So first off, just look back at all these trig derivatives that you know. Remember, derivative of sine is cosine, derivative of cosine is negative sine. Derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. And then we've got secant and cosecant. Derivative of secant is secant x tan x. Derivative of cosecant is negative cosecant x cotangent x. Remember, the way I kind of remember those is, since tangent and secant go together with the derivatives, it makes sense that they're all together here, positive, because it's positive secant squared. And cosecant and cotangent seem to always match up. And since cotangent's derivative is negative cosecant, it's also negative down here. Okay, so the first part here is just some practice with all of these trig derivatives in a lot of different forms. First example is y equals x sine of x. So make sure you recognize this as product rule. There's two variables. There's an x there and an x there. It's part of this bigger function of sine x. So it's really like x times sine of x. So I've got to use product rule. Anytime I use product rule, I always say first, which is x, times the derivative of the second. The derivative of sine of x is cosine of x, plus the second, which is sine of x, times the derivative of the first. Derivative of x again is 1. And there's not really a lot of simplifying we can do. I like to rewrite it without all of the extra little multiplying dots in there. So y prime is x cosine of x plus sine of x. And that's your final answer. Now remember, I mentioned once before, but you can always check derivatives using your calculator. So if I wanted to check this derivative, I could put in y1, x sine of x. In y2, I could draw the derivative by doing n derived, so math 8. The derivative with respect to x of y1. Oops, wrong spot. Sorry about that. Let's try it over here. For all values of x, we're going to put x down there. And then if we want to see if that's the same as this answer we got over here, I just got to type in x cosine of x plus sine of x. Now this is the original function, this is the derivative, and this is another expression for the derivative. So y2 and y3, if my answer is correct, should be the same. I don't really care about seeing what the graph of y1 is, so I'm going to move up here and turn that off. So I go highlight the equals, hit enter, that turns it off. I'm in trig, so let me make sure I'm in radian mode. Hopefully I am. Yup. So if I just go, I'm going to go zoom trig, zoom 7, and there is what the calculator determines the derivative to be. And if that's the same as our line, we should see it match up completely, and it does. So that's a quick way to check, especially if you're in a multiple choice question on a calculator test, what the derivative is. Okay, moving on, next one. Y equals 4 cosine of x. Now you actually don't need product rule if there's no variable. So 4 is just a constant. And we did do a rule a while back where the derivative of a constant times a function is just the derivative of that function times the constant. So that 4 just stays multiplied out in front, and then I take the derivative of cosine, which is negative sine of x. So multiplying that, I get y equals negative 4 sine of x. So off here I wrote there's no need for product rule when you're multiplying by a constant. I could do the first, which was 4, times the derivative of the second, negative sine for cosine, plus the second, which is cosine, times the derivative of the first, but when I take the derivative of 4, I just get 0. So this whole second piece goes away anyways. That's why we don't really have to use product rule when we're multiplying by a constant. I still can, it's just extra work. Okay, number 3, y equals x squared minus sine of x. So this is not a product, it's just subtraction, so I just take the derivative of each piece separately. So the derivative of x squared is 2x, minus the derivative of sine of x, which is just cosine of x. That one's kind of boring, not much going on there. That's our answer. Okay, now I get y equals sine of x over x. This is a quotient rule. So it's obviously a quotient. I can't simplify it at all, so I'm stuck with quotient rule. So y prime equals the bottom, which is x, times the derivative of the top. The derivative of sine is cosine, minus the top, which is sine of x, times the derivative of the bottom. And the derivative of x is 1, all over the bottom, which is x squared. So I can't really do too much to even clean that up. Y prime is going to be x cosine of x minus sine of x all over x squared. Now I think the quotient rule is probably the fastest way here, but there is another way to think about it. I could think about it as 1 over x times sine of x. That's the same as sine of x over x. And remember, 1 over x we'd rewrite as x to the negative first. So I could do a product rule with it. I could say the first times the derivative of the second, derivative of sine is cosine, plus the second times the derivative of the first, negative x to the negative second. And cleaning that up, this is just 1 over x cosine of x. This is the same as saying, keep that negative up top, negative sine of x over x squared. Was that negative 2 power there? And then if I got common denominators, multiply this by another x, I get that x cosine of x minus sine of x all over x squared. Same thing I got. So you can look at it either way you want. I think quotient rule makes this one a little bit easier. Okay, next page. F of x equals 1 plus sine of x over 1 minus sine of x. What do you think about this one? Don't be tempted to multiply by the conjugate. That's a trick we used with limits. That's not necessarily going to help us as much with derivatives. I'm not trying to simplify, I'm trying to take the derivative. So, let's use quotient rule. F prime of x equals the bottom, which is 1 minus sine of x, times the derivative of the top. And the derivative of the top, the 1 would go away. Sine of x becomes cosine of x, minus the top, 1 plus sine of x, times the derivative of the bottom. 1 goes away again. Minus sine of x becomes minus cosine of x, all over the bottom squared. 1 minus sine of x squared. Now this one I'm going to multiply out the top to start simplifying. So otherwise I can't really see how stuff combines. So I'm thinking that I'm going to distribute this cosine of x in here. Same over here with this negative cosine of x. So that's going to look like cosine of x minus sine of x cosine of x. When you distribute this negative cosine, it would be negative cosine, but there's this extra negative out front. So it's going to turn it into a positive cosine of x. And this would be negative sine cosine, but with this extra negative, it's plus sine cosine, all over the bottom squared. And if you notice, we've got 2 terms here, negative sine x cosine x plus sine x cosine x. Those are gone. I can add cosine x plus cosine x. I get 2 cosine x all over 1 minus sine of x squared. And there's nothing more I can do. That's my answer. Now this bottom is not equal to cosine squared x. How come? Because the squared is on this whole piece. If it was 1 minus sine squared, if I could look like that, I could change it into cosine squared. It doesn't say that. I'd have to actually multiply this out or box it out. So that's why I'm just going to leave it. Okay, number 7. Find the derivative at x equals pi if y equals sine of x cosine of x. Now notice over here I said product rule. They're being multiplied. You've got to recognize that. So the derivative dy over dx. I would take the first, which is sine of x, times the derivative of the second. Derivative of cosine is negative sine, plus the second, which is cosine of x, times the derivative of the first. Derivative of sine is cosine again. Oh, sorry, just kidding. All over. What am I doing? That's it. Okay, so this becomes negative sine squared of x plus cosine squared of x. Now this one wanted me to evaluate it specifically at pi. So the derivative, dy over dx, evaluated at x equals pi, would be negative sine squared pi plus cosine squared pi. And we got to evaluate that. Pi's over here. This is point -1, 0. So this is negative sine of pi. Sine is the y value, so that's 0 squared, plus cosine of pi is -1, again squared, because of these. That's 0 plus 1, so my final answer should be 1. Now remember that I can check really easily also. If I do a quick little end derive with that, I can just go y equals, what was my original? Sine x cosine of x. Sine x cosine of x. So we'll get rid of these other things. I don't need them anymore. And if I do math 8, so the derivative with respect to x of that function, vars, y vars, function y1, at x equals pi. When we get that number, remember rounding it works a little weird with end derives, so that's going to be essentially 1. So that confirms our answer there. Okay, last one like this, and we got to talk about something new. This one's a tricky one. 2 sine x tan x all over secant x. I could think of this as, hopefully you're seeing, quotient rule. So I would have f prime of x equals the bottom, secant of x, times the derivative of the top. Now the top's annoying. What's the derivative of the top? Product rule. So I'd have to do, to get the derivative of the top, I got to say the first 2 sine of x times the derivative of the second. Derivative of tangent is secant squared of x, plus the second, which is tan of x, times the derivative of the first, and derivative of 2 sine of x is 2 cosine of x. So far that was just the bottom times derivative of the top minus the top, so 2 sine of x tangent of x, times the derivative of the bottom. The derivative of secant is secant x tangent x, all over the bottom secant x squared. Okay, that's looking pretty ugly. What I'm going to do next is, I've got this secant x out front of this part. If you think of distributing everything, that might make things look a little bit, at least, better in the sense that I know what I've got. So I'd have 2 sine of x secant cubed x plus 2 secant of x cosine of x tangent of x. That's just taking this secant and distributing it. Over here, that's all one big piece. So it's minus 2 sine x secant x tan squared x all over. I'm going to write this as secant squared x. Now the reason I did that was to see what I could factor out at the top. I've definitely got a 2 in every term, and I also have a secant. I have 3 secants there, 1 there, 1 there. So I can pull out 2 secant of x, and that leaves me with 2, oops, sorry, the 2's out, took that 2 out. That leaves me with sine x secant x plus cosine x tan x minus sine x tan squared x all over secant squared x. Now you might be stuck. There's definitely one thing I can do. I can say this secant goes away with 1 down here. But we can also maybe clean up this part a little bit. Oops, I'm sorry, I just noticed I only took out one of these secants, so that's secant squared right there still. This piece right here is actually equal to sine of x. Let me show you why. So cosine of x times tangent of x. Tangent is sine over cosine. So see why that's really just sine? Okay, so if that's just sine of x, then technically I can take a sine out of everything. So in my next line, we still have this 2. Now I'm taking a sine of x out. That leaves me with secant squared x plus, this whole thing was sine of x, that's just 1 now, minus tan squared x all over secant of x. Now, anytime I see secant squared and tan, I start thinking 1 tanning is secant. So if I've got a secant squared x minus a tan squared x, like I have here, bring that over, it's equal to 1. So these two together are equal to 1. So now I've really just got 1 plus 1, which is 2. So this whole piece becomes 2 sine x times 2 over secant of x, which is really 4 sine of x over secant of x. But what's secant? Secant's really 1 over cosine. So this is 4 sine of x over 1 over cosine of x. And finally, I can complex fraction that. 4 sine x cosine x. Now you'd think I was done, but when I see sine x and cosine x next to each other with a factor of 2, what if I wrote this as 2 sine x cosine x? Does that make you think of anything? It's a double angle formula. So this is really 2 sine of 2x. How awful was that? Super awful. So pretty tricky, a lot going on there. And I'm not necessarily saying if this was a short answer, you'd have to know to get to that point. But if this was a multiple choice, like on your take-home test, maybe it'd be hard to recognize that the answer that you got way back here is really just the same as 2 sine of 2x. But that's the process I would go through. Okay. We're going to back things up a little bit, try something a little bit different. See how we're doing on time here. Oh, plenty of time. Okay. So the last page is this thing called chain rule. What the chain rule is it's a way to differentiate functions that are composed, composition of functions. Remember, composition, f of g of x. We've done that this year, we've done it previous years too. The chain rule says if you want to take the derivative of a composition of functions, you have to take the derivative of the outside function, so f prime, keep the inside function evaluated inside there, so we didn't change anything with that. So the derivative of the outside function times the derivative of the inside function. Now that's this official formula. We're going to have to use that sometimes, but I don't generally think of that when I'm using a chain rule. Here's some examples. Find the derivative of each. F of x equals x squared plus 1 to the 4th power. Now you could multiply this out 4 times and just take the derivative that way, but that's going to be really annoying, especially when I ask you to do it to the 9th power. So this is a composition. There's 2 functions here. We have f of x equals x to the 4th, and g of x equals x squared plus 1. X squared plus 1 is plugged into f of x to get x squared plus 1 to the 4th. But when I look at this, I just think of this as it's some stuff raised to the 4th power. That's what I'm saying over here. It's stuff raised to the 4th power. Well, what's the derivative of when something is raised to the fourth power? And we just use power rule. We take the 4, usually this is just x, and then subtract 1 to the third power. If there's more than just x in there, I just leave it alone. But it's not fair to totally ignore it, so I multiply it by its derivative afterwards. Here's what it looks like. So, again, don't really think of this for a second. Just think of it as 4 whatever to the third power. But the whatever was really x squared plus 1, so that got left alone. So now I got to multiply it by the derivative of that piece I ignored initially. That's why it's a chain, it keeps going. So the derivative of x squared plus 1 is 2x. I can clean that up a little bit because I can do 4 times 2x to get 8x times x squared plus 1 to the third. Second one. This time I've got stuff raised to the 9th power. So first I'm just thinking if it's stuff to the 9th, it's 9 times whatever stuff to the 8th power, but then multiply by the derivative of stuff. So here the stuff is 3x plus 2. Bring that 9 out front. So f prime of x would equal 9 times whatever that stuff is to the 8th power. And then I got to multiply by the derivative of that inside stuff. What's the derivative of 3x plus 2? It's just 3. So I get 27 times 3x plus 2 to the 8th power. Okay, last one for today. Radical stuff. Well, as soon as I see a radical, what do you think of? Hopefully you're thinking that this is the same as 5x minus 9 to the 1/2 power. So now it's kind of just like the other ones. I've got stuff raised to the 1/2 power. So I bring that 1/2 out front, subtract the exponent by 1, leaving that stuff alone initially, but then I multiply by the derivative of that stuff at the end. So f prime of x would become 1/2 times that stuff to the negative 1/2. So I just did power rule. I didn't really think of that stuff inside. And then I multiply by the stuff inside. Derivative of that stuff inside would just be 5. So this is really 5/2 times 5x minus 9 to the negative 1/2. But that's super ugly. I wouldn't want to leave it like that. We would just say this is, there's a 5 on top, a 2 on the bottom, and the negative 1/2 means that there's a radical 5x minus 9 on the bottom. There's our answer. All right, so we'll do more with chain rule tomorrow. It's not on your quiz that's on Wednesday this week. But you can now do problem set number 32. So make sure you're looking at problem set 32, and that's due Friday. So fill it in on that blue assignment sheet. And if there's time left in class, you can start working on that problem set. Good luck.